SPI, shortly we can call this as a serial peripheral interface. And we can also call in some books, they call this as a standard peripheral interface. So we can call this as a serial peripheral interface here for now. And this is mainly used for synchronous serial communication. So synchronous serial communication of the data. It's used for short distance communication, for example, within components of the PCB. Okay, so this SPI interface, it consists of 4 wires. So here you can see CLK, that is the clock, and the MOSI, MISO, and SS. So SPI is using 4 wires. And remember, SPI you can use in the master mode or slave mode. So for example, here we have the master SPI and we have the slave SPI in this example. So we are going to transfer the data serially between this master and slave. So here we have this clock signal. The clock signal is used to synchronize the data transfer. The data transfer between 2 different components. So maybe this SPI master is inside the microcontroller. This SPI slave may be external world in the another component. Okay, so this clock signal is synchronizing the data transmission between these 2 blocks. And the MOSI means master output serial input. So this wire helps to transfer the data from master device to slave device. So it's helping to transfer the data from master to slave. That is MOSI. And MISO means master input serial output. So this wire is helping to transfer the data from slave device to master device. So once you transfer from here to here, of course, maybe you need to receive even some acknowledgement and so on, right? So you must need, it's a bidirectional communication. So you are also sending some data from slave to master using this MISO wire. And we also have the SS. SS means that is a slave select. So in serial peripheral interface, we have only one master, but there can be several slaves. So maybe this is slave 1 and this is a slave 2 and maybe this is slave 3. Slave 3. So this master will select which slave it's going to communicate with. So here, for example, slave 1, this one is active low mode. So it means this master wants to communicate with this slave 1. If this master want to communicate with the slave 2, then the corresponding SS signal will be active low. Then it means the master wants to communicate with his slave 2, and then the data transfer will occur. So just to remember, SPI, it has 4 wires, clock, MOSI, and MISO, and SS. So each one has its own purpose. So there is only one master and more than one slave. So that is the SPI, the speciality of SPI, serial peripheral interface. It will have only one master, but it will have more than one slaves. So master can only initiate the data transfer either from master to slave, or slave to master. Only master can initiate the data transfer. Slaves cannot do that. And before master can communicate with slave, master must activate SS wire of the corresponding slave. So for example, here you can see this master has 4 signals, right? Clock, MOSI, MISO, and then SS1, SS2, SS3. Each SS wire is corresponding to one slave. So SS1 is connecting to this slave 1. SS2 is connected to slave 2. SS3 is connected to slave 3. So if it enables this SS3, then it means the master wants to communicate with this slave 3. Either master can send the data to slave or slave can send the data to master. So Here you can see how the data transfer is occurring between the master and slave. Here we have one master, and here we have only one slave. So here we have 8-bit data registers. So we have 0 to 7 registers. 0 to 7 registers. This is the LSB and this is MSB. Least significant bit, most significant bit. And here also we have this clock for synchronization. MOSI, transfer data from master to slave. MISO, data transfer from slave to master. So this is the data frame. So the MOSI, you can see here the datas, the bit 0 to bit 7, bit 0 to bit 7. This is just indicating the position, bit 0 position, the first position, the second bit position, third bit position, and so on. And it needs clock cycles. So for example, if you have 8 data in this master, 8 bits in this master block, you want to transfer all these 8 bits to this slave, then you need 8 clock cycles. So it means, so the first clock cycle, I transfer the MSB. It's a serial data transfer. So this, for example, in the 7th bit position, maybe this is a bit 0. Then it will come to this LSB, bit 0. And then this is the first clock cycle. Maybe I put in the rising edge. And then second clock cycle, the second rising edge, this is 1 clock cycle. And this is the second clock cycle. And then the third clock cycle. So for each clock cycle, 1 bit will be transferred. So this bit will be moved to the next register. Now this register is empty. Then the second, so once this one is finished, then this, whatever the data is here, it will be moved to this register, and this data will be moved to here. So this is a serial data transmission. The bits will be transferred one by one, bit by bit, serially. Not all the bits are transferred in parallel. So because this is the serial peripheral interface, this SPI is helping only the serial data communication. So there are shift registers in both master and slave, because all the registers and memories, they are just using the registers. Okay, so in both master and slave, which are connected by MOSI and MISO wires in a ring topology. So MOSI and MISO wires. So we have studied about ring topology last semester. We have studied about bus topology, ring topology, mesh topology, and so on. So the ring topology means it will be just like in the circular mode. It will be transferring the data between these 2 blocks. So data will move from master to master shift register to slave shift register. After 8 clocks, master and slave extends the register value. So after the 8 clock cycles, the first data frame is already transferred. Then the next transfer will start if this master is updated with the new data. So 8 clock cycles are must to transfer one complete data transfer between master and slave. And clock edges can be configured either in falling or rising, or both edges. So, and also please see here, here this is in the active low mode. It means when this SS signal is helping the master to select the slave. So when it makes the active low, it means 0. Then the data transfer occurs between this slave and this master. So here, then the clock signal will start, SCLK, serial clock. Each clock will help to transfer one data from master to slave. So for example, MOSI, this to slave. In the picture, it looks like, in the timing diagram, it looks like the data is transferred in parallel, but it's not true. It's transferring bit by bit in serial. So there are shift registers, the same thing. The only difference here, okay. So master sends character A and slave sends character B. So these two are the same like the previous slide. So what is the difference here? Here I had seen the standard template. Here we are seeing the example of the data frame. So always we have the start bit, and stop bit. So anyway, so start and stop bits are not important here now. So here we are seeing how we are transferring the data. So the master is transmitting, the MOSI is transmitting character A, ASCII character. So if you convert into binary value, it will be like this. And then the MISO is transferring the character B. So the MISO is different. So the binary equivalent of this character B is this one, 100000010. And here you can see 100000010. This slave is transferring this character B to master, and it's using 8 clock cycles for the data transfer. The data transfer occurs, each bit transfer occurs based on the rising edge. And here this, during the entire data transfer period, this SS wire is in the active low mode. It means it helps to transfer the data between this master and slave. This SS is indicating this slave. So here you can see the serial peripheral interface. What we are doing here, SPI1. So I am enabling this SPI1 under the full duplex master mode. Full duplex means both master and slave can have the data transfer. It's a bidirectional data communication. So we have also studied about the half duplex mode, full duplex mode, and so on. So half duplex means it can be the unidirectional. Even in the full duplex, you can say like both master and slave can communicate or transfer the data, but maybe not at the same time, only one at a time. But here we have the dedicated wire for master to slave and dedicated wire for slave to master. So master can send A at the same time. The slave can also send data to master. So both can do at the same time. Not like if for example, if it shares only one wire, then master first it should send the A. After receiving the data, then the slave will use the same wire and transmit the data again. That is the half duplex. And the full duplex means like we can do the bidirectional data transfer at the same time. It's not like a walkie-talkie. Okay, so now we enable this SPI1. So once you enable the SPI1, you should also know here, these 3 pins will automatically enable. So here if you can see PA 5, 6, 7. So these 3 wires, one is for MOSI, one is for MISO, and one is for the clock. So this is what we have studied just before the theory. So whenever we enable this SPI, we need to have 4 wires. And these 3 wires are very important. The SS is not showed here. The MOSI, MISO, and clock you can see. Okay, so these 3 pins, and then you are configuring the SPI in the full duplex mode. And of course, you can go to the data sheet and you can see more detail of these pin descriptions. Each pin, how it works and the functions and so on. So now I'm configuring the pin in the GPIO. So PB0, this is the output push-pull mode, and the PC15 we are using for the pull-up under input mode. And here you can click this SPI because you already activated SPI. In the SPI, everything you can keep it as a default. So here you can select the maximum, the prescaler value for the baud rate. So once you, if you change this prescaler value, you can see the baud rate will also change. Okay, so then you can generate the C code afterwards. Then once you generate the C code, then you can explore this SPI and the data communication.